This is your presenter, Asloob Mudassar, and I am presenting slide number 12B of the course on atomic and molecular physics. Today's lecture is in continuation of the previous lecture covered in slide number 12A. Today I shall be talking about the following topics: spin magnetism, spin angular momentum and spin magnetic moment, and their precession in applied magnetic field. In the previous lecture, I covered these things. That is, I talked about the orbital magnetic moment. This is its vectorial expression, and this is another form of its vectorial expression. That is the expression for the orbital magnetic moment of the electron. And then this is equation number 12.12 is in the magnitude form. So this is UL, that is the orbital magnetic moment in terms of its magnitude. And you know that the quantity on the right hand side is the magnitude of the orbital angular momentum. In equation number 13 and 16, on the right hand side, the vector L represents the angular momentum, orbital angular momentum of the electron. Now this is the Z component. When you apply the magnetic field, then the Z component of the UL, that is the Z component of the orbital magnetic moment of the electron, is given by minus GL mu B into ML, where ML is the orbital magnetic quantum number. And if you want to take the maximum of this quantity, you need to take the maximum on both sides, and the maximum value of ML is represented by the orbital quantum number. So in equation number 18, on the right hand side, this L represents the quantum number. So the maximum value of the Z component of the orbital magnetic moment of the electron is equal to minus GL times Bohr magneton times the orbital quantum number. Then in equation number 25, this relationship was reported, that is the magnitude of the orbital angular momentum is equal to the square root of the orbital quantum number L times L plus 1, and outside that one we have h bar, which is the reduced Planck constant. So in equation number 25, on the left hand side, this L represents the quantum number, and on the right hand side, this L represents the quantum number, orbital quantum number, and on the left hand side, this represents the quantity. On the left hand side represents the magnitude of the orbital angular momentum. Then in equation number 24, the relation Lz is equal to MLH bar. Lz is the Z component of the orbital angular momentum in the presence of the magnetic field, or because the magnetic field has the same direction as that of the Z axis, or the Z axis has the same direction as that of the magnetic field. So Lz is the Z component of the angular momentum, which is given by ML times h bar, where ML is the orbital magnetic quantum number. And this ML has the following possible values. ML is equal to 0, plus minus 1, plus minus 2, and so on up to plus minus L. So ML has a maximum value equal to plus L or minus L. ML is the magnetic quantum number. So you see that in the previous slide, I talked about orbital angular momentum of the electron, that is this L vector, orbital angular momentum of the electron. And then we also talked about the orbital magnetic moment of the electron and their mutual relationships. Then the Z component of this orbital angular momentum, then the maximum value of the Z component of this angular momentum, then the relationship between the magnitude of the angular momentum of the electron with its orbital quantum numbers, and then with the Z component, the relationship of the Z component of the orbital angular momentum with the orbital magnetic quantum number of the electron, and then their relationship, the allowed values of ML in terms of the maximum values plus minus L of the orbital quantum number of the electron. So these were covered in the previous lecture. So I repeated them because you will be encountering similar expressions in the today's lecture for the spin case. Now you see that previously I talked about the orbital angular momentum, that is orbital quantity. Now I am talking about the spin angular momentum and spin magnetic moment, and what will happen in the presence of the applied magnetic field. These things will be talked about, and I shall also be talking about the spin quantization. So the today's lecture starts now. The existence of directional quantization was established by the Stern and Gerlach experiment. So directional quantization means that the direction of the quantities that I am going to talk about is fixed in space, and its magnitude is also fixed. So let's talk about the spin and magnetic moment of the electron. So you see that spin is this is the first time that I am talking about the spin thing. You see that here I shall talk about the spin quantum number, I shall talk about the spin angular momentum, I shall talk about the spin magnetic moment, and I shall talk about what will happen to these quantities in the presence of the applied field. So here I am going to talk about spin and magnetic moment of the electron. Individual alkali metal atoms have a single s electron. This is what we have seen in one of the previous lectures. So individual alkali metal atoms have a single s electron in their outermost shell, which is unpaired and are paramagnetic. All the alkali metal atoms are paramagnetic because they have outermost valence electron as the s electron, which is unpaired electron. This single unpaired electron creates a magnetic moment, and the individual alkali metal atoms are attracted to the applied magnetic field. So you see that if you apply the external magnetic field to these alkali metal atoms having only s electron as the valence electron, and being a paramagnetic material, individual atoms of the alkali metal atoms are the paramagnetic materials. They have their own magnetic moment, and in the presence of the external magnetic field, they will be attracted towards that magnetic field. Alkali metal atoms in bulk form. Now you see that here I am talking about in bulk form. Not before that, in the previous paragraph, I talked about the individual alkali metal atoms. Now here I am talking about the alkali atoms in bulk form. Have valence electrons leaving their atoms and form a sea of electrons. So you see that the s electron is present in each of the alkali metal atoms. So when you have a bulk sample, then these electrons may leave some of these s electrons may leave their atoms and form a sea of electrons. Many electrons pair up in the energy bands of the bulk material, while a small number of electrons near the Fermi level will be unpaired, and thus the material is weakly attracted to the applied magnetic field, because most of them may be paired in the energy bands and some of them will be unpaired near the Fermi level, and due to that one the material is weakly attracted toward the applied magnetic field. Alkali atoms in bulk form a weakly paramagnetic material. Alkali singly ionized atoms. So you see that there is an inner core of electrons and there is one valence electron which we call as the s electron. So if you singly ionize the alkali metal atoms, then you lose the s valence electron and you have a closed shells of electrons only in which the electrons are paired up. So in the closed shells, when the alkali metal atoms are singly ionized, you are left with the closed shell of electrons, and each of these electrons in the closed shell will be paired up, resulting in the magnetic moment equal to 0. And thus, such materials are diamagnetic materials. So singly ionized alkali metal atoms are diamagnetic in nature. That is, they are not attracted towards the applied magnetic field, or the applied magnetic field has no influence on the singly ionized alkali metal atoms. Now this is the picture, this is the real picture that I have presented, giving you the definition of the paramagnetic material, weakly paramagnetic material, and then the diamagnetic material. Now what is happening actually? For s electron, orbital angular momentum is equal to 0. That is, the value of L is equal to 0, or the magnitude of the orbital angular momentum is 0 for the s electrons. And also the orbital angular momentum mu L is equal to 0. You know that mu L is related with L, as we have seen some equations before the start of this lecture, that there is a relationship that mu L is related directly with the L vector. So when the magnitude of the L is 0, then of course the magnitude of the orbital magnetic moment of the electron is also 0. So for the s electrons, magnitude of the orbital angular momentum is 0, and thus the magnitude of the orbital angular momentum, orbital magnetic moment is also 0. But according to this one, the s electron atom should be diamagnetic. So if we apply this definition, that is the magnitude of L is equal to 0 and the magnitude of the magnetic moment is 0, then it means that the s electrons in the alkali metal atoms behave as a diamagnetic material. But that is not the case. These are still paramagnetic materials. That is, the single electrons are just the paramagnetic materials. But how this is possible? The problem is that we have not yet talked about the spin quantity. The reason is that we have not considered yet the spin s of the electron and the associated spin magnetic moment mu s. You see that in the absence of these two quantities, that is s and mu s, we cannot justify this statement that is given in this last paragraph. So it means that there were some quantities were missing. So these were the quantities, that is the spin angular momentum represented by s vector and the spin magnetic moment represented by mu s. These two quantities, we have not yet talked about these two quantities. So in the absence of these quantities, it is difficult to justify the statement given in the last paragraph. So we are now going to talk about the spin angular momentum and the spin magnetic moment. Uhlenbeck and Gauss-Smith in 1925 introduced spin angular momentum S in order to explain the spectroscopic observations. Because at that time there were some observations which could not be justified. So Uhlenbeck and Gauss-Smith in 1925 introduced the concept of spin angular momentum and spin magnetic moment, and their contributions was parallel to the concept introduced for the case of orbital angular momentum and the orbital magnetic moment. Splitting of many spectral lines in the presence of the magnetic field, that is, in the presence of the applied magnetic field, could only be explained if an electron has a spin angular momentum s. So if you apply the magnetic field, then there is a further splitting of the spectral lines, and that could only be explained if we concentrate on the concept of the that there is a quantity which we call as a spin angular momentum represented by the vector s. And this is the relationship between the magnitude of the spin angular momentum written on the left hand side and the spin quantum number written on the right hand side under the square root sign. So under the square root you have s into s plus 1, and outside that one you have h bar. And the spin magnetic moment similarly has a relation is equal to minus gs into E over 2 m naught multiplied by the vector s. These two relationships are exactly the same as written for the case of orbital quantities. So similarly, generalizing the concept of the orbital quantities for the spin quantities, we have these two relationships. So on the left hand side in equation number 29, you have the magnitude of the spin angular momentum, and on the right hand side the quantity s is actually the spin quantum number. And in equation number 30, on the left hand side you have the spin magnetic moment, and on the right hand side you have this s vector, which is the vectorial form of the spin angular momentum. So equation number 30 is in the vectorial form, where the spin quantum number S defined on the right hand side of equation number 29 is the spin quantum number. It has a fixed value S is equal to half. So S is equal to half is the spin quantum number. The new factor Gs you can see in equation number 13 is the so-called G factor of the electron. And similarly, it has, and similar to the orbital case, its initial value may be assumed to be equal to Gs is equal to 1, is the value based on classical theory. But the empirical value is Gs is equal to 2.0023. So the empirical value measured from the spectroscopic data reveals that the Gs has a value equal to 2.0023, whereas its classical value is Gs is equal to 1. You see that in the previous cases, we have seen that the electron revolves around the nucleus and forming a current loop where the orbital angular momentum vector L is perpendicular to the plane of the electron loop. But here we are talking about the spin. Spin is similar to the rotation of the Earth about its own axis. So in the figure you can see that the electron is spinning about its own axis. M naught is the mass of the electron, E minus is the charge of the electron, and this electron is spinning about its own axis like the Earth spins about its own axis. And you see that when it spins about its own axis, a quantity which is called spin angular momentum is produced, which is perpendicular to the axis of rotation, which is perpendicular to the plane of the rotation of the electron. And the other quantity, which is spin magnetic moment represented by mu s, is a quantity opposite to the spin angular momentum and is shown below with a vector pointing downward to the direction of the s vector. So you see that similar vectors were given for the case of the orbital angular momentum and orbital magnetic moment, but that was the case because those quantities were perpendicular to the plane of the loop where the electron oscillates. But here these two quantities are perpendicular to the axis, to the plane where the electron rotates about its own axis. Spin angular momentum and the spin magnetic moment of the electron with charge E minus and the mass m naught are shown. So you see that electron also spins about its own axis and giving you the concept of spin angular momentum S and the spin magnetic moment represented by mu S. So what happens? What will happen to this figure? That is the figure that I have shown over here. You see that the direction of S is not fixed because the electron can rotate, can spin about its own axis, and this axis are not fixed. So electron is not bound to give you its spin angular momentum in the vertical direction. So S can have any direction, but it is always perpendicular to the plane of this electron, plane of the rotation of the electron about its own axis. So S and mu S will always be perpendicular under this condition, but their direction, that is the direction of S and mu S, are mutually at 180 degree to each other, but their directions are not fixed in space. So if you apply the magnetic field to the electrons, what will happen? This condition will arise as shown in the figure. That is, this is the electron, and this is the vector S of the electron, that is the spin angular momentum of the electron. Now under the application of the magnetic field B, which is applied in the vertical direction, which we also called as the z-axis, this spin angular momentum will start its precessional motion about the magnetic field. So this is the loop. The loop indicates that this is the precessional motion and it is defined by the tip of the spin angular momentum. So the spin angular momentum defines this loop, and the spin angular momentum carries out a precessional motion about the magnetic field. the magnitude of the S will remain fixed, and the angle that the vector S makes with the direction of the magnetic field will also remain fixed, while the S vector starts with its tip the precessional motion about the magnetic field B. And the component of vector S along the B direction, which is only a component measurable, is the SZ component. So SZ is actually the projection of the vector S on the Z axis or in the direction of the B magnetic field. So in principle, S has three components, sorry, Sx, Sy, and Sz. The Sx and Sy components are averaged out during the motion or during the precessional motion of the vector S about the magnetic field. These two components, that is Sx and Sy, will be averaged out and cannot be measured. The only component that can be measured experimentally is the Sz component of the spin angular momentum. So that's why I have shown only that component. And you know that the magnitude of vector S is given by S into S plus 1, the square root of S and S plus 1. And you know that the value of the spin quantum number is half. It is a fixed quantity. So half into half plus 1 under the square root multiplied by the h bar is actually will give you the magnitude of the spin angular momentum. And you know that the spin magnetic moment will be directed opposite to the direction of this vector S, which I have not shown, and that will also carry out the precessional motion about the magnetic field. I have not shown the vector mu S, which is the spin magnetic moment of the electron, but that is directed opposite to the vector S, and that will also spin about. Similarly, we will trace out a spinning loop like the vector S has shown in the upward direction, but that vector, that is the mu S vector, will spin about the minus B direction or minus Z direction. Now you can see this dotted line. I have also shown a vector with a dotted red line in the downward direction. This vector S, that is the spin angular momentum, can have two orientation. For example, it could have an orientation as shown in the upward direction, that is in the direction upward to the location of the electron along the direction of the magnetic field. It will precess about the direction of B, about the B positive direction. And equally, it is also possible that when you apply the magnetic field, the vector S is located in the downward direction. So if S is found in the downward direction, it will carry out a precessional motion about the minus B direction or about the minus Z direction. So if you apply the magnetic field, there is a probability that the S vector is located as shown in the present case, or S could be located in the form as shown by the dotted red arrow. So two situations are equally possible for the spin angular momentum. Okay, now you see that the Z value of the spin angular momentum is given by half h bar, and this is half h bar because it is related with the spin magnetic moment. Ms is the spin magnetic moment of the electron. You see that here I have introduced a new quantum number, ms. Ms is the spin magnetic quantum number, like the ml, which was the orbital magnetic quantum number, which I have discussed in the previous lecture. Now this is the spin magnetic moment multiplied by the h bar, and the ms value is equal to either it is equal to plus half or is equal to plus half. So ms can have only two values. You know that the spin quantum number S has only one value, which is half. So S is equal to half is the value of the spin quantum number, and the spin magnetic quantum number has two values. Ms is equal to plus half, or it can have a value equal to minus half, as shown below. So ms can have both possible values, so equally possible, plus half and minus half, depending upon the spin angular momentum is directed upward or directed downward with respect to the direction of the magnetic field B. So under the external magnetic field B, the spin angular momentum S has its component along the Z direction labeled with SZ. It is equally probable that S, that is the spin angular momentum, carries out precessional motion either along plus B direction or along minus B direction. You know that if it is carrying out the precessional motion about the plus B direction as shown by the solid vector S, and the dotted vector S shown will carry out the precessional motion about the minus B direction. The value of this Z component is determined by the spin magnetic quantum number, and the spin magnetic quantum number will have only two values, ms is equal to plus minus half, because it is equally probable that ms can have its value plus half or minus half. That is the orbital angular momentum. Spin angular that is the spin angular momentum is either pointed upward or pointed downward. This is equally probable under the application of the magnetic field. So ms has two possible values, ms is equal to plus minus half. So about the, when you talk about the z component of the spin angular momentum, which is sz, it is equal to ms times h bar, and ms is equal to plus minus half. So you see that we are similarly defining, as in case of orbital quantum number, we have similarly defined the spin quantities. We have defined the spin angular momentum. We have defined the spin magnetic moment. We have defined the spin magnetic quantum number, and also the spin quantum number, in a similar pattern that we have discussed for the case of the orbital quantities discussed in the previous lecture. Dirac in 1928. Spin of an electron is a necessary consequence of the relativistic quantum theory. And you know that the Schrödinger equation is non-relativistic. And we have treated the problem of the hydrogen atom using the Schrödinger equation. But you know that complete relativistic quantum treatment was not given. So if you follow the complete relativistic quantum theory, you will come out with the concept of the spin of the electron. So the spin of an electron is a necessary consequence of the relativistic quantum theory. And if you follow that quantum theory, you will get the value of Gs equal to 2. You know that classically we have set the value of Gs is equal to 1. But if you follow the Dirac theory of the relativistic quantum theory, you will find out that the value of Gs is equal to 2. It differs from the empirical value, which can only be understood if the interaction of the electron with its own radiation field is taken into account through quantum electrodynamics. So you see that this is the value that we have found from the relativistic quantum theory, Gs is equal to 2. But later we shall see that Gs is equal to 2 will be modified by its empirical value, which will be Gs will be equal to 2 point something. And that can only be explained if we take into account the interaction of the electron with its own radiation field. Then we can find out the exact value of the Gs, which will also be satisfied, which also satisfies the empirical values. Empirical values mean that the values obtained by the analysis or by the spectroscopic analysis of data. By the spectroscopic data analysis, we can find the empirical values. So you see that quantum electrodynamics treatment is required if you want to find out the exact value of the Gs parameter of the Gs that would also satisfy the empirical value. Now you see that this is the vectorial definition that I am going to give you of the spin magnetic moment is equal to minus Gs times E over 2m0 times the spin angular momentum in vectorial form. So this is the definition in vectorial form. And if you want to take the z component, you need to take the z component on both sides. So on the left hand side I have mu sz, and on the right hand side I have sz. So these are the z components of the vectorial equation. Now mu sz is equal to minus Gs I am multiplying and dividing with H bar. So I have E H bar over 2 M naught, and similarly I have S Z over H bar, because I want to introduce, I want to replace E H bar over 2 M naught by the quantity which is called Bohr magneton mu B. This is mu B has also been defined in previous lecture. So I am not going to follow, I am going to follow similar concept discussed in the previous lecture. So the Z component of the spin magnetic moment is equal to minus Gs times Bohr magneton times Ms times H bar, because the value of Sz is equal to Ms times H bar divided by H bar. H bar will cancel out, and I have this quantity on the right hand side, which is minus Gs times mu P times Ms. So Gs is a constant, is an empirical, is a constant that is adjustable according to the parameters. So classically its value is 1, and according to the quantum relativistic theory its value is found to be equal to 2, but its empirical values is given below, which is its empirical values is different, which is given over here. So Z component of this so the Z component of the spin magnetic moment is equal to plus minus 1.00116 into mu b, because Gs value was divided by the value of Ms, because Ms has two possible values plus minus half. So Gs was divided by plus minus half, and you got this value. So the actual value of Gs will be equal to this value multiplied by 2. So 1.00116 multiplied by 2 will give you the actual value of Gs, because here in this equation we have divided the value of Gs by the values of Ms, which is equal to, which are equal to plus minus half. That's why you have plus minus over here in equation number 33. So equation number 33 will give you the Z component of the spin magnetic moment in terms of the Bohr magneton connected through the constant plus minus 1.00116. During the precessional motion of the spin angular momentum or the spin magnetic moment, their Z components stay constant, whereas the other components, that is their X and Y components, will average out to 0 because of the spinning of the electron. Now let's talk about the gyromagnetic ratio, which from equation number 16 we have for the case of the orbital magnetic moment. We had this quantity discussed in which we have discussed in equation number 16 and reproduced over here. That is the orbital magnetic moment of the electron was mu L. Mu L is equal to minus GL mu P into L vector over H bar, and this can be represented as minus GL mu B over H bar into L vector. So this is in the vector, this definition is in the vectorial form. And here you can introduce, you can introduce gamma function, gamma L instead of GL mu B over H bar, as shown in equation number 34. So GL mu B over H bar has been replaced by gamma L, and we have chosen a positive sign, because we have chosen the magnitudes over here, and we can take a positive sign over here. So gamma L, which is the gyromagnetic ratio for the case of the orbital case, has been defined over here in equation number 35. So gamma L is equal to magnitude of the orbital orbital magnetic moment divided by the orbital angular momentum. Similarly, for the case of the spin, we can define gamma S. Gamma S will be equal to the magnitude of the spin magnetic moment divided by the magnitude of the spin angular momentum, as shown in equation number 36. So we can also write in terms of the parameters, if you substitute the value of magnitude of mu L divided by the magnitude of L, if you substitute the value, these values, you will get gamma L is equal to GL mu B over H bar, which we have also defined in equation number 34. So this is the value of gamma L. Similarly, we can define gamma S, that gamma S is equal to Gs times Bohr magneton divided by H bar, as shown in equation number 38. So gamma is different for orbital magnetism and spin magnetism. You can notice these expressions given in equation number 37 for the case of the orbital case, and in equation number 38 for the spin case. So these quantities differ only by the parameter GL and GS. So we can also write equation number 37 in the following form: gamma L multiplied by H bar is equal to gamma L multiplied by mu B. And this can also be written as mu B provided GL is equal to 1. So GL will be equal to 1 for the pure orbital magnetism. That is, if we ignore the case of the spin magnetism, we shall get the value of GL is equal to 1. The pure orbital magnetism can be obtained when we have two electrons as the valence electrons, where the two electrons where the spin of the two electrons will cancel each other when they have anti-parallel spins. Under that condition, we will have the pure orbital magnetism. Under that condition, the value of GL will be equal to 1. Now we can also write the equation number 12.38 in the following form, that is GS multiplied by H bar is equal to GS times mu B. And here the value of GS is equal to 2.0023 times mu B. This is the value of GS that we have obtained from the previous expression we have written over here, because this value in equation number 33 multiplied by 2 will give you the actual value of GS, which we have shown over here in equation number 40. So GS H bar is equal to 2.0023 times mu B. And here the value of the GS is equal to 2.0023. This is the value of GS under the case of pure spin magnetism. And this is pure spin magnetism case will arise under the case when the orbital angular momentum L is equal to 0. That is for the case of S electron. So when the S electron will be present as the spin as the valence electron, then of course the orbital angular momentum of the electron will be 0, and such a case will be called as the pure orbital angular momentum or the pure orbital magnetism. Under such a condition, the pure spin magnetism will arise, and its value and the value of GS will be equal to 2.0023. So for the case of the pure orbital magnetism, and for the case of a pure spin magnetism, you can notice the equations. So you can notice the parameters in equation number 12.39 and 12.40. To calculate the magnetic properties of atoms, measurement of either gamma or G is required. So you see that the next thing we have used gamma and G parameters. So if one of them is known, the other parameters is also known. So we need to find out these constants, that is either gamma or G, experimentally. Gyromagnetic ratio by Einstein-de Haas method. So this is the experiment in which the gyromagnetic ratio is measured. So let me first of all explain you the experimental setup. This experimental setup consists of a rigid spot, and there is a string hanging, which you can consider as a metallic wire on which the mirror is mounted, and this is the material which could be magnetized. You can consider it as a magnetizing material, and you are applying there is a coil which is wound around this magnetizing material, and this coil is called a magnetizing coil, because when you pass the current through this magnetizing coil, it will magnetize the material. And then of course tiny atomic magnets will also be magnetized, and they will carry out their precessional motion, like the individual electrons will carry out their precessional motion, and due to that one, a twist is in the wire is produced and a mirror is rotated. And this is a source. You can also consider this source as a narrow beam of light projecting light on the mirror, and this light is then reflected on towards a scale, and the scale can be used to measure the deflection under the application of the magnetic field. So now let me go through these the paragraphs that I have written down over here. An iron needle is magnetized by a coil. While the magnetic field is changed, the magnetization of the sample is changed. So you see that when you change the magnetic field, the magnetization of the sample is also changed. Change in magnetization changes the direction of the atomic magnetic moments in the sample. You see that we have discussed the atomic magnetic moments. We have discussed two types of magnetic moments: orbital magnetic moments and spin magnetic moments. But here we are not talking about the specific one. Here we are keeping the magnetic moments in the general form, because these magnetic moments can stand as a sum of both magnetic moments, or as the superposition of those magnetic moments. So change in magnetization of the needle changes the direction of the atomic magnetic moments in the sample. So let me read this paragraph under the figure, that if the magnetization is changed by 180 degree by reversing the polarity of the coil, the angular momentum vector must also be rotated by 180 degree. So you see that in this sample, the angular momentum, when the magnetic moment is switched to 180 degree, the polarity of the magnetic coil is switched to 180 degree, then of course the angular momentum, all the angular momentums of the individual atoms in this material will be rotated by 180 degree. So when the direction of the magnetic moments change, a change in the angular momentum of the whole sample is observed as per law of conservation of angular momentum. So you have the individual atoms, and if their magnetic moments are reversed due to the by reversing the polarity of the field applied to the coil or applied to the material, then all atomic magnets will reverse, and of course the overall their sum will give you the total angular momentum. There will Some will give you the total magnetic moment which will also be reversed in direction. And when it will reverse its direction, then of course a twist or a reverse is indicated by the rotation of this mirror, and then on the scale we can measure that quantity. That is, the rotation could be measured. Quantitatively, the change delta mu n in the magnetization of the needle can be represented as the sum of changes in the magnetic moments of the individual electron. This delta mu n is actually related with the magnetic moment of the whole sample. So delta means change in magnetic moment of the whole sample. So this delta mu n can be represented as the sum of the changes in the magnetic moments of the individual electrons, which is written in equation number 41. So delta mu n is equal to sigma summation over 1 to n delta mu z, where delta mu z is the z component, is the change in the z component of the magnetic moment of the atom. And if you sum up all these mu z components, that is, if you sum up the changes in all the mu z components, you will get this quantity equal to n times 2 mu z, which is explained in the next equation. So you see that here we are connecting a macroscopic quantity with the microscopic quantity. So mu z is the microscopic quantity, and mu z is the z component of the magnetic moment of the atom under the application of the magnetic moment, under the application of the magnetic field. In the measurement, a detection coil and a ballistic galvanometer are used. I have not shown these two instruments, that is the detection coil and the ballistic galvanometer has not been shown. These are used in the setup to measure the change in the magnetic field, and the ballistic galvanometer is also used to measure the current flowing in the coil. These have not been shown over here. If the magnetic field is reversed, all magnetic moments in the material flip into opposite direction. This causes a change in magnetization, and this change in magnetization has been explained over here. So delta M is the change in magnetization. So this M is the magnetization in the presence of the magnetic field, capital M, and this minus M, which we have subtracted from capital M, is actually the magnetization, change in magnetization when we reversed the polarity of the magnetic field by 180 degree, then of course the magnetization will be reversed also. So there is a negative sign over here, and then we have M minus times minus M, it will be equal to 2M, and this 2M is actually 2N times mu Z, because the magnetization of the material is actually the sum of all the Z components in the material, in the sample which we are considering that there are N electrons in that sample. And so you see that 2 times 2 is coming because of the change in magnetization, and we have N electrons, and each electron has a magnetic moment equal to M equal to mu Z. So this relationship is N into 2 into mu Z. This is what I have shown in equation number 41. So you see that when we change the polarity of the magnetic field, then of course delta mu N will be equal to N into mu N into 2 into mu Z, where mu Z is still unknown. Whereas this delta mu N has been measured experimentally using the detection coil and the ballistic galvanometer. So delta mu N is known. On the left hand side quantity is known. On the right hand side we have the quantity which is mu Z is unknown. If the change in angular momentum of the needle is delta Ln, this is the change in angular momentum of the needle measured by means of the torsion fiber, which we have shown in the experiment. For example, this thread is actually the torsion fiber, and if the change in angular momentum of the needle is delta Ln measured by means of the torsion fiber, the sum of the changes of the atomic angular momenta, which is given by this relationship. So delta Ln, that is the change in the magnetic and the change in the angular momentum. You see that the previous equation was that is equation number 41, dealt with the change in magnetic moment. And here we are talking about the quantity which is the change in angular momentum of the sample is equal to the summation over from 1 to n of delta Lz, where delta Lz is the change in the Z component of the individual atom. And this is equal to 2 times 2 into Lz, similar to the case that we have discussed in equation number 41. And here Lz is the Z component of the orbit, or is the Z component of the angular momentum. Here Lz is the Z component of the orbital angular momentum. So you see that delta Ln, so you see that here is the Z component of the angular momentum, of the orbital angular momentum. But look at this equation. Here we have not specified the magnetic moment, because here magnetic moment is kept not fixed with orbital thing or with spin thing. So this mu may start both for orbital and for the spin case. That's why I have not used any subscript with it with mu. I am not using L with mu, neither L nor S with the mu quantity. So it means that this mu quantity could stand for both orbital magnetic moment and both for spin magnetic moment, or both for the sum of these two quantities. But here I am specifying Lz because this quantity is only related with the z component of the angular momentum. So delta Ln can be measured by means of the torsion fiber, whereas delta mu n is measured using a detection coil and a ballistic galvanometer. So you see that the left hand side of both equations, that is the equation number 41 and equation number 42, are known. So the left hand side of both quantities are known, and the right hand side of the quantity 42 has been measured through. So the left hand side of both quantities are measured. So let's see what happens next. Now we are calculating the ratio of delta mu n over delta Ln, which is equal to n times n into 2 into mu z over n into 2 into Lz. So some quantities will be considered out, and we have mu z over Lz. So this mu z over Lz is equal to E over m naught. Because if you specify the value of mu z and Lz from this lecture and the previous lecture, you will see that substituting those values over here, you will get E over m naught. And then E over m naught is nothing but gamma. Because gamma is the ratio of the electron to the mass of the electron, ratio of the charge of the electron to the mass of the electron. And you know that the charge of the electron and the mass of the electron are known, so gamma quantity is also known. So from equation number 23, we had this expression that gamma is equal to G into mu B over H bar. You see that here again, we are not using any subscript over here. We are keeping this equation in a general form, which may stand both for orbital thing and also for the spin quantities. So gamma is equal to G into mu B over H bar. We can rearrange this equation as a G into E over 2 m naught. And we can divide this equation with 2. So we have G over 2 separated from E over m naught. And you know that E over m naught is again gamma. So it means that G over 2 is equal to 1. Because on the left hand side we have gamma, and on the right hand side we have G by 2 into gamma. So it means that G by 2 is equal to 1. So G over 2 is equal to 1, which means that G is equal to 2. So this is the value that we have found experimentally. Using experimental data, we have found the value of G is equal to 2. Experiment reveals that there is an angular momentum associated with the magnetism of the atom. The detailed analysis may indicate how much of the magnetism in a given sample is due to spin angular momentum and how much is due to orbital angular momentum. So you see that it is very much evident from this experiment that there is a quantity which is we call as angular momentum is associated with the magnetism of the atom. That is, if you apply magnetic field to an atom, a quantity associated to the atoms will be the angular momentum or the magnetic moment. The detailed analysis may indicate, which we are not covering in this course, the detailed analysis may indicate how much of the magnetism in a given sample is due to spin angular momentum and how much is due to orbital angular momentum. This is still unknown. That's why sometimes we kept the data without using the subscript as L or subscript as M as S, because we were unaware how much the contribution to the angular momentum is due to spin or is due to orbital thing. Detection of directional quantization by Stern and Gerlach experiment. You see that in the previous experiment, we have measured the physical quantities, but we have not just talked about the directional quantization. That is, are the direction of these quantities fixed or not? In the experiment given by the Stern and Gerlach, we are going to discuss the directional quantization of the magnetic moment or the angular momentum in the presence of the applied magnetic field. So when there is no magnetic field, there is no quantization of the angular momentum of the or the magnetic moment. But when you apply the magnetic field to the atom or to a given sample of atoms, then what will happen? These quantities, that is the angular momentum and the angular momentum and the magnetic moment of both the quantities are quantized, and they start their spinning motion about the magnetic field. So in 1921, deflection of atomic beams in inhomogeneous magnetic field was observed. Deflection of the atomic beam was observed in the inhomogeneous magnetic field. This is important. So if the magnetic field is homogeneous, there will be no deflection of the atomic beam. So under the inhomogeneous case, you will see a noticeable change in the deflection of the atomic beam. This was observed, which led to the conclusions that the demonstration of directional quantization of atomic magnetic dipoles, that there are atomic dipoles, atomic magnetic dipoles, to which we have a quantity associated as magnetic moments, and under the application of the applied magnetic field, there is a directional quantization of these magnetic dipoles. Direct measurement of the magnetic moments of the atoms. So you see that this experiment also provides the measurement of the direct magnetic moments of the atoms in the beam. So a beam of silver atoms was generated in an atomic surface, in an atomic furnace, and collimated by a series of slits. So the beam was generated, the beam was slightly diverging. So a number of slits, focusing elements were used. Electromagnetic fields were applied to the beam so that the beam could be focused or narrowed down. Then a number of slits were used to narrow down the atomic beam so that the beam could be passed through inhomogeneous magnetic field. A beam of silver atoms was generated in an atomic furnace and collimated by a series of beam. Collimated beam, that is the beam which is not diverging, having the constant diameter, is called a collimated beam. The beam was passed through a highly inhomogeneous magnetic field with a beam direction perpendicular to the field direction. So this is important, that the beam that you are passing through the magnetic field, that is you are passing through the inhomogeneous magnetic field, should be perpendicular in direction to the applied magnetic field. When there is no magnetic field, the magnetic moments and the angular momenta of the atoms are randomly oriented in space. In homogeneous field, these vectors, that is mu and L, precess about the magnetic field direction B. This is what we have seen earlier, that if you apply a constant homogeneous magnetic field to the atoms, the two quantities, that is the dipole, that is the magnetic moment of the atoms and their orbital and their angular momentum. Here in this case, I am specifically talking about the orbital angular momentum will start precessional motion about the magnetic field. But you know that in this experiment, we are talking about the inhomogeneous magnetic field, and through that one, we are passing over a beam of collimated beam of silver atoms. In an inhomogeneous field, the deflecting force can be derived from the magnetic potential energy. You see that when the beam of a magnetic moment mu will pass through the magnetic field B, the magnetic energy that will be stored will be equal to Vg, V mag mean potential energy due to the magnetic field will be equal to minus mu dot B. This expression is what we have also considered in the previous lecture, and this is equal to minus mu b cos of alpha, where alpha is the angle between the direction of mu and the direction of b. So mu cos alpha can be combined as the z component. So mu z represents mu cos of alpha. That is the component of alpha. That is the component of mu in the b direction. So let me show you the experimental setup first, and then I shall go ahead. First of all, I show you. So let me read this one. Setup of the Stern and Gerlach experiment. An atomic beam passes through an inhomogeneous magnetic field. The beam splits into two components after passing through the field. So you see that this is atomic beam. The atomic beam was generated. This is the atomic beam of the silver atom or the hydrogen atom generated in a atomic furnace, and a collimated beam was generated using many slits. One of the last slit is shown over here. So after this slit, the diameter of the atomic beam is nearly constant. The beam passes through inhomogeneous magnetic field. From these lines of the magnetic field, you can see that the magnetic field is inhomogeneous because these lines are curved. Moreover, these lines are not parallel to each other, so indicating that the magnetic field is inhomogeneous. And you can see that I have shown partial derivative of B with respect to Z, which means that if you move along the direction of the Z, then of course you will find that the magnetic field is inhomogeneous with the direction of Z. And you know that this beam of silver atom is passing through horizontally, and is passing through in a direction perpendicular to the z direction, whereas the inhomogeneous magnetic field is applied to the along the direction of z. And then you will see the result is that if you have the classical result, mean that there is no quantization. The magnetic moments of individual atoms are randomly placed. They are not aligned. They have random directions, and this is the classical result that we should obtain. But you know that under the application of the applied inhomogeneous magnetic field, the beam has deflected because the force on the beam was acting upward. A part of the force was acting on the beam in the upward direction along the z direction, and the part of the force was also acting along the minus z direction. Due to that one, half of the beam has deflected upward and half of the beam has deflected downward. So indicated by the beams which arrive at the top end and the bottom end of this oval shape area. So there are deflection along the positive z direction and along the negative z direction. This is what we are going to understand. Why are these deflections there? And we are going to take advantage of this potential energy, magnetic potential energy, because we can derive the force from this potential energy. The force that will act upon the atoms is given by this one. So alpha is the angle between mu and B, and the force along the z direction will be equal to the minus partial derivative of the magnetic potential with respect to the z axis will be equal to mu z times dB over dz. So in the previous equation, I have just taken the derivative with respect to z. And I have substituted back the value of mu z, which was mu cos of alpha. And the derivative of dB over dz is present over here. So it means that you can see that this force, which will act upon the z direction, is equal to mu into cos of alpha into dB over dz. So if alpha is 0, then you have cos of alpha is equal to 0, mean that cos is 1, and mu dB over dz, that is this force will has a component along the positive b direction. But if you have alpha is equal to 180°, cos alpha will be equal to -1, and this force will be directed downward opposite to the direction of z axis. So depending upon the value of alpha, so if alpha is 0, the force will be upward. If alpha is equal to 180°, the force will be downward. So a magnetic dipole is oriented parallel to the magnetic field. Alpha is equal to 0, moves in the direction of the increasing field strength, that is along the positive z direction, while the anti-parallel dipoles with alpha is equal to 180° moves towards the lower field strength. You know that the spin has equal probability to be aligned, have spin upward and the spin downward. Using the spin magnetic quantum number ms has two values, plus half and minus half, which indicates that there is a equal probability, half probability for the spin quantities, for the spin magnetic moment or the spin angular momentum to align upward along the d direction, and half have the probability to align downward along the minus b direction. So half of them will precess about the positive b direction, and half can precess about the negative b direction. So since both are present, so half of them will be aligned along the positive b direction, and half of them will be aligned along the negative b direction. And those dipoles which are perpendicular to the b direction, having alpha is equal to 90°, will not be deflected. So you see that I have explained that the force will act on these molecules, on these atoms of the silver beam or the hydrogen beam, and half of them will be deflected along this positive direction, and half of them will be deflected along the negative z direction or along the negative b direction. So you see that this is the signal that we have observed. This signal in the blue in the center is the signal which indicates that it is the signal in the absence of the field. So when the field is not present, then of course you will measure a case like this one, which is called as expected result. That is, the beam is not deflected. The beam diameter will not be changed, and the two parts of the beam which have been shown as deflected will not deflect and will concentrate on the center. So this is the central part is the undeflected part, and this will be due to the absence of the magnetic field. So when you apply the magnetic field, then of course the beam will be deflected as shown by the red curve in the presence or with the magnetic field. So you can notice that there are two peaks over here. These two peaks indicate that some of the beam is going over here, and some part of the beam is located over here. And in this particular setup, the separation between these two is 1 millimeter. So this on the horizontal axis, we have the position of the detector wire, which measures the strength of the concentration of the arrivals of the silver beams, of the atoms of the silver beams. And on the vertical direction, we have the galvanometer signal measured, which is connected to the direct detector wire, and the signal was measured on the galvanometer. So observe the intensity distribution of an atomic beam with and without an applied magnetic field are shown. The atoms of the atomic beam were in the state 2s half. That is, the valence electron was the s electron. And you know that when we have the s electron, Then we have the orbital angular momentum is equal to 0. We have only the quantities which are related with the spin. And you have the two quantities related with the spin angular momentum and the spin magnetic moment. And here you see that when you apply the magnetic field, you know that there are two possibilities that we have discussed due to the spin magnetic quantum number ms have two possible values plus minus half. That is why we have the half probability to be located or deflected upward and half of the probability to be located downward. So you see that this confirms the concept that the probability that the quantum number ms is equal to plus minus half is predicting truly the magnitude of these quantities. Okay, classically, any orientation of alpha of the atomic magnets with respect to the field is allowed. This is a classical result. In classical picture, one thus expects a continuum of possible deflections. So there is no particular deflection. So classically, we should expect that the deflection will have a continuum value. That is, a continuous deflection could be observed. So, but with the hydrogen atom or with the silver atoms, two sharp peaks separated by two delta were observed on the detector. Because with the hydrogen atom and with the silver atoms, you have in the outermost shell you have s electrons. And with the s electrons, you have orbital angular momentum is equal to 0, and you have only spin related quantities. Now I am giving you some conclusions based on this experiments and on many other experiments similar to this one. So this and similar other experiments yield the following conclusions. Number one, there is a directional quantization with two discrete possibilities, parallel and anti-parallel to be. Delta is measured from the experiment. In addition, if the field gradient, that is delta B over that is dB over dz, is known, then mu z plus minus mu B is also found. So mu z can also be measured if we could measure precisely the value of this inhomogeneous magnetic field, which we are not reporting. So it has come to us from a similar as a conclusion from many similar experiments. For all atoms having s electrons as the outermost electron, the value of the deflecting force is the same. This means that the angular momenta and magnetic moments of all the inner electrons cancel each other. You know that there could be many inner electrons within an atom, within an atom's outside of which the s electron is present. For all these inner electrons, the two quantities, that is the magnetic moments and the angular momentum for the inner electrons, will cancel out each other, and one measures only the effect of the outermost s electrons. So for all the inner electrons forming closed shells, the value of the total orbital angular momentum and the value of the total magnetic moments for such electrons is 0, located in closed shells about the nucleus. The s electron has orbital angular momentum L is equal to 0, and one observes only the spin magnetism. Atoms maintain magnitude and direction of their angular momentum in space during motion. So you see that in the beam, the electrons traveled the distance through the inhomogeneous magnetic field, and they retained their direction and they retained their magnitudes and direction also. So this is what the concept of quantization of these quantities. So you see that in the today's lecture, I have discussed these quantities. I have discussed quantities like spin angular momentum, spin magnetic moment, spin quantum number, spin magnetic quantum number, ms. Then I have discussed similar relationships of these quantities. That is the relationship of the spin magnetic moment with the spin angular momentum. I have also described that these two quantities are oppositely directed due to the presence of the negative sign between these two quantities in their vectorial form. And these two quantities also precess about the magnetic field, and that the spin can have two orientations, one along the magnetic field and other along the minus magnetic field. So described this experiment for the gyromagnetic ratio by the Einstein-de Haas experiments, which confirms the magnetic dipole moment, calculation of the magnetic dipole moment, and then the quantization of the quantities, especially the spin quantization, was established by the Stern and Gerlach experiment, was also described in this experiment. But you know that this lecture is continued, which the remaining part will be described in the next slide. So up till now, this is the end of slide number 12B of the course on atomic and molecular physics.